Here we are looking at a 25,000 microfarad capacitor rated at a maximum of 25 volts. Right now we have it connected to the power supply set to 5.6. It's in series with this light bulb. When I make the connection to the power supply, a short flash of light occurs and the capacitor is charged. If I connect over here to the bulb directly from the capacitor, another flash of light and the capacitor is discharged. Now, it does not take a long time for it to charge or to discharge, charge or discharge, and we can see the light bulb light either way. The direction of the current would be opposite. All right now we have it hooked up to a LabQuest with a voltmeter connected straight to the capacitor. Now, if I start recording data and I charge, notice that the voltage rises very quickly to the value of 5.6. When I discharge, we get the flash of light and very quickly back down to 0 volts. All right, charging again, rises to 5.6 volts, drops down to 0. Now notice on here that it does take a little bit of time for the capacitor to charge. Not instantaneous, but a very short period of time. Let's replace the light bulb with a 150 ohm resistor. Now, it has a lot more resistance than the light bulb did, and we expect that the charging will take longer. Right. Now, in this case, we don't see any flash of light, but we do see that the capacitor is growing in its voltage as it approaches 5.6 volts. It's approaching full charge. It's going to take some time and longer now because of the higher resistance of the resistor. And then eventually the capacitor becomes fully charged and it levels off at 5.6 volts. 5.6 volts. Now, if we do the same thing in reverse, that is, discharge the capacitor through the resistor, let's watch that curve. All right, now the capacitor is being discharged and the voltage is dropping back down to 0. The voltage starts out at 5.6 volts and it approaches 0 volts as the capacitor discharges. This is called exponential decay. So the charge in here is decaying and the voltage across it is also decaying. Remember that Q equals C times V, capacitance times the voltage. So the amount of charge we could figure out in here would be C, 25,000 microfarads, times V, 5.6. And that's how much charge is in there, and we slowly let that charge drain back through the resistor. All right, let's look at a mathematical model that describes this. This is our mathematical model that's going to describe the discharging of the capacitor. Y equals E, that's Euler's number used for a base of natural logarithms, raised to the power of negative x. Negative x. Now, if I wanted to solve this for x or negative x, I would just take the log of e to the negative x and I'll get negative x. Now, what would this graph look like if I plotted y and x on a xy graph? To complete this chart, I could use a calculator and the e raised to the x button. It's the second function of the natural log button. So hit the second, e, and then it waits for me to put my exponent, in this case negative 0, and I get 1. If I put in e raised to the power of negative 1, I get 0.37. Let's round it to 2 decimals, 0.37. So let's fill in our chart now with this data. Okay, here's our completed data table. Now notice that I added one more piece of data to show that once we get past 5, x equals 5, then we would have to go out to 3 decimal places to see that it is in fact not exactly zeroed yet. So for practical purposes, we're going to say once we get past x equals 5, we're pretty much going to be at 0 for our y value. Next, we should make a graph of these data. Okay, here's the graph of these data. This is what we call an exponential decay. We start out at our starting value, in this case simply 1, and then over time that diminishes or decays down to 0. Now, how quickly it decays kind of depends on this exponent, negative x. Now, for the other graph, we're going to use these values of e raised to the negative x, but what we're going to do is take 1 minus each one of these values here. All right, so 1 minus 1, of course, is going to be 0. 1 minus 0.37 is going to be 0.63, 0.63, 0.86, 0.95, 0.98, 0.99, and we'll go from there. After x equals 5, we're almost 100% of our way back to 1. Let's make a graph out of that. All right, here's our graph. Now this one is showing an exponential growth toward a specific value, in this case approaching 1. So they're kind of like inverses of each other. All right, these two mathematical models then are how we model the charging and the discharging of a capacitor. Let's take a look at that. Here's a schematic diagram of a RC circuit. It consists of a resistor and a capacitor and an EMF, a voltage source. And then we have what's called a single pull double throw switch. When I throw the switch to position A, current then can flow through the circuit, charging the capacitor. Electrons will come out of one side, flow through the resistor, and around. The capacitor will become charged in position A. If we put the switch to position B, then the charge that's in the capacitor can then go the other direction and discharge through the ammeter and the resistor. Now, however much charge we put on the capacitor in position A, we'll get that same amount of charge back out, and the current will flow in the opposite direction. All right, let's take a look at how these graphs would play out then. First, let's consider charging the capacitor. And that would put the switch into position A. Now, right when the switch is closed, a large amount of current will flow, and that amount of current will depend on the EMF and the resistance. So when the switch is first closed, we get a certain amount of current flowing, and then as the capacitor reaches charge, that current's going to drop down to 0. The current will drop down to 0. Once the capacitor is charged, then it just behaves like an open circuit, and the current will stop, and we will have a charged capacitor. Now, if I put a voltmeter across the resistor, then that will measure the voltage on the resistor as it's charging. I could also put a voltmeter across the capacitor. Let's call that VC, and then we'll call this one VR. Now, what would these voltages look like? Now, when the switch is first closed, current is high, and the voltage across the resistor is just going to be I times R. Whatever the current is going to determine how much voltage is across the resistor. So at the start, when the current is high, that voltage will read whatever the source voltage is. So the voltage across the resistor will start out at whatever the voltage source is, and then it will diminish. The voltage across the capacitor will grow. It will grow, and that will approach all of the voltage, the EMF. So the voltage across the capacitor would follow this pattern. The voltage across the resistor would follow this pattern. The voltage on the resistor will decay, and the voltage on the capacitor will grow up to the source voltage. Now, each one of these follows one of those mathematical models. So the decay one, where we had y equals e raised to the power of negative x, instead of y here, we're going to have I, and then we're going to have a certain amount of current at the beginning multiplied times this factor, e raised to the negative x. All right, now what is x? X is time. X is time. So instead of x, we'll have time. And what time will that be? So there's where we're going to use the time constant. So time is going to be ticking away in increments of the time constant. So instead of x, I'm going to write t for time divided by RC, the time constant. So the exponent will be increments of RC. So when t equals RC, then we have a -1. When t equals 2 of RC, then we have an exponent of -2. So our exponent is going to be in increments of RC. So if we put that on the graph, then we would start out, of course, at time t equals 0, and then we're going to have 1 increment of RC, and then we're going to have 2 increments of RC, and then 3, and then 4 increments of RC, 5 increments of RC, etc. on there. So the exponent is growing in increments of RC. Now, once we reach 5 values of RC for all practical purposes, we are going to say the capacitor is fully charged. Once we reach 5 time constants. Now, of course, we could continue on, and the voltage, say, on this kind of graph is just going to level out, and all of these will level out. So once we get past 5 time constants, we're going to say that the capacitor is fully charged. Now, let's look at a discharging graph. For a discharge, then once it's charged, we would turn the switch from position A to position B, and now the current that originally charged the capacitor will flow out in the opposite direction and discharge the capacitor through the resistor. So the voltage on the capacitor starts off at whatever it ended at full charge. So the voltage across the capacitor is going to start off at the EMF voltage, and then it will diminish as the capacitor discharges, and the voltage across the resistor will be exactly that same voltage, but in the opposite direction. So we might call it, say, negative EMF. So it would start off, and then as the capacitor loses charge, then of course that will also follow this. Now notice that that's opposite of this EMF on there, so that we can make it fit on the same graph as well. Now the current, right when we close the switch to position B will be up at its maximum, whatever that is. Again, that's going to be E over R, the initial. Now this will be in the other direction, so we'll call that -2 as well. And it will start off high and shrink down to 0 once the capacitor reaches full charge or loses all of its charge. Now we could also look at a graph for the charge on the capacitor during the charging process and during the discharging process. And during the charging, the capacitor is going to start off at 0 charge, and it will grow to a value that is equal to Q equals C times V. C times V. And V will be the EMF. Now, during discharge, the capacitor starts off with that charge of C times V, and then it will slowly lose its charge and follow the same kind of graph. All right, now graphs that are a decay follow that general equation, in this case Q equals Q0, which Q0 is going to be equal to C times V, multiplied times E raised to the power of -T over RC. All right, that's your discharge. The charging graph follows the equation Q equals Q naught, or Q0, 1 minus E -T over RC. A couple of more things. Let's say we have our graphs for the voltage across a capacitor for discharging or charging, or even the charging graph for discharging. Let's say we need to find out something like T at a certain value or V at a certain value. We could use our mathematical relationship, which is given here. Now, if we had to solve it for something in that exponent, eventually we'll have to take the log of E raised to the power of something, and then we'll get the something on there, and then we could solve for it either if we're looking for T or R or C or something like that. Now, look at this algebra right here. If I solve this for V over E, then take the log of both sides, I get the log of V over E equals -T divided by RC. Now this is actually in the form of a straight line. All right, we could make a graph out of this. If we made a graph out of this, we would graph the natural log of E over V and T on the x-axis. This should end up giving us some kind of a straight line. What would the slope of that straight line be? The slope of that straight line is going to be the reciprocal, or 1 divided by RC, the slope of that line, if we make a graph like this. Now, B is the y-intercept, and that would probably be 0 in this case, as there's no voltage already on the capacitor when we start the time. So at time t equals 0, the voltage on the capacitor is 0. Now, some textbooks will actually use a Greek letter called tau instead of RC. So if we use that kind of notation, then E would be raised to the power of T divided by tau. You see it like that sometimes too as well. Tau is just the symbol that we use for the RC time constant. Or we could just use RC and leave it as that.